All right. Hi, everyone. So today we are happy to have Alex May from Stanford University giving a talk about towards quantum information processing in gravitational system. Thank you so much, Alex. Please.
Okay, great. Well, yeah, thank you very much for the invitation. It's a great opportunity to talk to everybody here. So what I'm going to be speaking about is coming out of a whole sort of program or sequence of works that kicked off with this paper back in 2019. And this sort of program has grown over time in collaboration with a number of great people who are listed here. And most recently, I've been working with Sam Cree, who's a graduate student here at Stanford. What I'm going to talk about is sort of based on this whole perspective, but the technical results will be coming mostly from this upcoming paper with Sam. Okay. So I want to start out super generally by reminding you of one way that many people like to think about quantum information, which is that it's a theory that starts with a set of rules given to it by some area in physics, in this case, quantum mechanics, and then asks, subject to those rules, what are the consequences for information processing? Okay. From this perspective, I think it's natural to ask about other areas in physics and their consequences for information. So for example, in relativity, we have the no signaling principle that says that you can't send information faster than the speed of light. And beyond that, in quantum gravity, we think that there are additional constraints on information processing, but we understand them less well. So for example, there's a conjecture, which most of you will know, which is the covariant entropy bound. And what this says is that the amount of entropy that can pass through some region in space-time is bounded above by the area of that region. If that's true, that's again some kind of interesting information processing constraint, right, coming from quantum gravity. And I think what these kind of examples makes clear is that if we want to think about the physics underlying information, quantum mechanics is not the end of the story, right? And instead, since we think we live in a world that's described by some kind of a theory of quantum gravity, if we want to understand information processing at a sort of fundamental level, we should really be thinking about the physics of quantum gravity and what its consequences are for information processing. Okay, so that's the sort of question that I want to take up today. And I'll maybe say at this point that, I think what I'm doing here is sort of preliminary, and I'll try and be clear about what we know and what we're arguing for. But I'll also point out some places where I think we can say some concrete things, and we're getting some really nice hints that we're sort of on the right track. Okay. Good. Okay. So one of the big picture ideas that I'll try and emphasize today, and that I hope you'll take away from this talk, is that at least when we think about quantum information processing in the context of holographic spacetimes, we'll be able to translate questions about quantum information with gravity into other questions about quantum information without gravity, just by using the ADS-CFT correspondence. And I'll explain how you can kind of do that sort of translation. Okay. A bit more specifically, the kind of question that I want to address about quantum information processing in the context of gravity is about the limits of computation. Okay, so more specifically, I want to think about some kind of a finite space-time region, like say this little diamond I've drawn, and then consider some quantum systems coming into the region, some other quantum systems coming out. I want to ask what transformations can relate them. Is it just all quantum channels, as would be suggested if you just think about quantum mechanics? Or are there additional constraints on computation that come up when we think about the physics of gravity? Okay. In accordance with this kind of an idea, what I'm going to argue is that you can translate that gravitational question into a non-gravitational one about what's called a non-local quantum computation. Okay. And specifically into understanding how much entanglement is required to implement one of these non-local quantum computations. Okay. Another thing to emphasize here is that this subject of non-local quantum computation is in itself a very interesting and rich subject in information theory. And there's a number of reasons we might want to study it aside from this connection to gravity that I'm emphasizing. So one reason is, and the reason it was originally studied is actually a connection to cryptography. And there, this non-local quantum computation idea is related to this cryptographic scenario where you're trying to verify somebody's location in space. Okay. After that was thought about, it was fairly soon realized that there's also some interesting connections here between non-local quantum computation and both classical and quantum complexity theory. So I'll try and emphasize that as well. The results I'll give today will be mostly about better understanding non-local quantum computation. And one of the things that those results will do is sort of deepen this connection to complexity theory. And another thing those results will do will be to reveal a new connection to a different subject in quantum information, which is this idea of quantum secret sharing. Okay. So in the talk today, I'm going to start on the gravity side of the story here. And I'll try and explain this question and make it a little bit more precise. And then I'll argue using the ADS-CFT correspondence how we can understand this question in terms of this non-local quantum computation idea. And then in the later part of the talk, I'm going to sort of put on my quantum information theorist hat and think about just non-local quantum computation in itself, the connections to these various subjects, and then also how those various subjects then tie back into the quantum gravity side of the story. Okay.
Sorry, Alex.
Yeah.
How should we understand this? Is the idea that the states that describe important or physically relevant states of quantum gravity have a special entanglement structure that constrain the set of computations that we can do? I mean, quantum gravity is a quantum mechanical theory, right? So yeah. Supposedly constraining computation, you mean states that naturally appear and we care about have particular entanglement structure? Is that what it is?
Yeah, so okay, this is you're anticipating my whole talk. It's a great question. So yeah, as you say, in quantum gravity, in say ADS-CFT, there's just a quantum mechanical description of the whole thing. And so you could say, how does this make sense? Isn't it just quantum computation or quantum transformations? What we'll see is that computations that happen or transformations that happen inside of some restricted region are reproduced in a particular way in the conformal field theory. And the particular way that they're reproduced will rely on some entanglement properties in the conformal field theory. And we're going to try and use those to constrain what can happen inside of this region.
So, but supposedly those entanglement properties are properties of the low energy states of the CFT. Well, maybe you'll explain all of this. Sorry.
Yeah, bring that up again. I think I'm still confused about that point. So yeah, we should discuss this again. Okay. Okay, yeah. So let me basically say what I was just saying in response to Nima's question in more detail. Okay, so yeah, we're interested in this question. We have some gravitating region, and we have some quantum systems coming in, some quantum systems coming out. We want to know how they can be related. To put this in a bit of context in the literature, other people have thought about this. So most famously, Seth Lloyd back in 2000 thought about this question and argued that gravity would constrain the complexity of what could happen inside the region. And he had in mind specifically the circuit complexity. Okay. So how did he argue this? He wanted to use just two things. So he just took ordinary quantum mechanics plus one additional bit of physics coming from gravity. So the additional bit of physics was that he said the energy inside the region should be bounded above by the mass of a black hole with the same sort of size. Okay. Based on those two ingredients, he tried to upper bound the complexity. The argument is very plausible looking, but unfortunately the argument is actually wrong. And this was pointed out by Stephen Jordan in 2017, who gave a construction that in quantum mechanics implements an arbitrarily complex unitary arbitrarily quickly at arbitrarily low energy. Okay, so this argument of Lloyd's was not correct. But an important sort of caveat here is that both of these constructions, Jordan's and Lloyd's, ignores sort of the full context of quantum gravity, right? They're just saying, let's take quantum mechanics plus this energy bound. And so although Jordan showed in that context, there's no bounds on complexity, it's not clear that in the full picture of quantum gravity, when we think about things like no signaling and the covariant entropy bound, that there couldn't then be some bound on complexity. That's something I'm going to explore today. Yeah, so that's one question that I'll try and address.
Alex, are you going to mention say a few more words about this counterexample of Jordan?
I could, if you're interested.
I don't want to change the direction of your talk, so maybe afterwards.
Okay, yeah, it's a very, well, we can see how well I can reconstruct it in my head, but it's actually quite a beautiful construction. So, okay, so yeah, I'm going to try and address this question. To do it, we're first of all going to try and be a little bit more precise about what the question is exactly. The first step towards making this more precise is we want to be careful about how we define the region of interest. So there's some region, we're going to call it J. The computation is going to happen inside that region. I'm going to construct J in a particular way. Okay, in particular, the way I'm going to construct it is I'm going to pick 4 points, C0, C1, R0, and R1. And I'm going to construct J by taking intersecting future and past light cones of these points. So I've drawn this on the right. We have this point C0. I'm going to look at its future light cone, take the future light cone of C1, intersect them, the past of R0 and the past of R1, intersect all 4 of those, and that's going to define J for me. Okay. A region constructed according to this procedure, I'm going to call a scattering region. And I'm always in this talk going to focus on computations happening specifically within scattering regions. Okay. The other thing I need to do to make the question a little bit more precise is be careful about where the input systems start out and where the output systems should end up. And what I'm going to do there is I'm going to have input system A0 start out near C0, A1 start out near C1. They're going to come into the region somehow. They'll interact, some computation happens, and then the output systems should end up at R0 and R1. Okay, so this is just like a sort of minor rephrasing of the question. It removes a couple of ambiguities though, and will be important as we keep going. Okay. The next thing I'm going to do to address this question is I'm going to narrow the scope again and specifically think about scattering regions that are constructed inside of a holographic spacetime. Okay, so I've done that here. To construct the region, I pick my four points, right? I've made sure to pick them off at spatial infinity in ADS. Yeah, this is sort of an important detail. But anyways, I pick these 4 points. I look at their light cones. That will define for me some region J inside the bulk of my ADS space. I've drawn an example here where J happens to be just 1 point. That didn't have to be the case. In general, it will be some extended sort of a region with some shape to it. Okay. Yeah, so this is how the computation looks, or the picture for how it happens in the bulk picture. I'm going to also kind of summarize this with a sort of schematic diagram like I've shown on the right, which just captures the essential causal features. So here A0 and A1 come in, the yellow dot signifies some computation, whatever happens to them inside of this scattering region, and then they come out again. Okay, computations happening in that form, I'm going to call a local computation. Okay, so this is the local form. Okay. Now I want to look at the same process, but from the boundary perspective. So I pick the points off at spatial infinity, so I can identify them with points in the boundary manifold. So here they are again, C0, C1, R0, R1. And then we said that the input systems, A0 and A1, start out near C0 and C1 in the bulk picture. In the boundary, the same quantum information, the same data will be stored near these points I've identified in the boundary. Okay, good. So we have A0 and A1, B0 and B1, and the same overall transformation from inputs to outputs will happen in the boundary picture as happens in the bulk picture. Right. What's different though is how it happens. Okay. So in the bulk picture, we had this sort of a schematic where things come together. But that's not the picture of how things happen in the boundary. In particular, if you say try and bring A0 and A1 together like this, you can get out to R0, but now you're too late to get to R1, right? And similarly, if you try and meet up like this, you can get out to R1, but now not to R0, right? So this cannot be the right picture for how the computation happens. Instead, I claim that the right picture for understanding the computation is this thing on the right. Okay. Let me explain this sort of schematic picture on the right in a little bit of detail. So now we have this state on two systems, V0 and V1, that's shared between the left and the right. V0 is over here, V1 is over here. Okay. Then what happens is A0 and V0 interact in some way, A1 and V1 interact in some way, a round of communication is exchanged, and then there's another set of computations at the end. Okay. At the end of this process with the computation, the communication, and then a computation again, we're supposed to have reproduced the same computation as happened in the local form, right? The boundary reproduces the local computation in this sort of form. This form I'm going to call a non-local computation. Okay.
Sorry.
Yeah.
So let's say I think of these guys as some sort of like local quenches. So let's say at point C naught on the boundary, I do local quench.
Yeah.
So there will be sharp waves in the direction, spreading in the light cone.
Yeah.
Which roughly speaking, I can think of as like EPR pairs, right? Let's say it shoots EPR pairs, and yeah, exactly. And same thing for C1. Is that picture consistent? Because now you could causally affect both of the points R0 and R1.
Yeah, right. So good. So let me explain a little bit more how this schematic diagram maps into the space-time picture. So, okay, something happens. Let's start with the bottom left. There's this yellow dot that's representing some interaction between A0 and V0. So in the space-time picture, A0, I hit the CFT with some operator. It introduces some information there. A0 can spread into this future light cone. And this dot is representing a process that's in the future of C0 and in the past of R0 and R1, right? Because the output here gets to R0 and the output here gets to R1. So the way I want to think about this is that yellow dot represents everything that's happening in the causal future of C0 intersected with the past of R0 and the past of R1. And so that's this diamond like this. So we introduce some information on A0. V0 represents some of the degrees of freedom in the CFT, and specifically the degrees of freedom in this diamond here.
Yes.
And then similarly, there's V1 over here. Okay. And the entanglement. So in general, this state that starts out shared between the left and the right will be some entangled state. And that entanglement is capturing the entanglement between these parts of the CFT.
Right. I see. Thank you.
Yeah. Yeah, good. Okay, so the sort of punchline from the last two slides, right, is that every computation that happens inside of the scattering region in the bulk picture is reproduced in the boundary picture in this non-local form. Okay, and the way that I want to think about this is as some kind of a constraint on what can happen inside of the region, inside the scattering region. So we can only do things inside the scattering region that can be computed non-locally in the boundary. Right. That's our constraint. I want to make that a little bit more precise and in particular quantitative. To do that, I'm going to introduce a sort of a quantity of interest on the bulk and the boundary side. On the bulk side, what I'm interested in is the area of the scattering region. So I've drawn a scattering region here in its sort of extended form when it's not a point. It looks like this tetrahedron. The tetrahedron has four faces. That has to do with the four light cones coming from these two input and two output points. The details of the geometry aren't super important. What you do want to know, though, is that there's sort of this privileged edge along the bottom of the tetrahedron. And it's that thing's area that I'm going to keep track of. Okay, so I'll call that A sub R. And yeah, just a reminder here that because I'm in low dimensions, the area is the length of that one-dimensional line. Good, so that's the bulk quantity. In the boundary, the quantity I want to keep track of is the correlation in this shared state between the left and the right. And in particular, I'm going to think about the mutual information of that state.
Sorry, can I ask a question?
Yes.
So do you expect, let's say in the bulk, do you expect this to be a Lorentz invariant quantity, or so can you say, for example, suppose I have one cubic centimeter and 1 centimeter in time. You can factorize, let's say, primes up to some size, and then if you wait longer, you can do more computations, but if you have more volume, can you do also more computation in shorter time?
Yeah, so the area of this thing is a well-defined quantity. So this surface R I could define in terms like causally, so it would be I don't know, I mean, it's not super important how it is, but it's the boundary of the future of C0 intersected with the boundary of the future of C1 intersected with the past of R0 and the past of R1. So this length is like diffeomorphism invariant, for instance. You were then asking, like, does it sort of make sense that this thing's area would control what computations can happen inside the region? It's hard for us to know, like, from a bulk perspective, what should control what can happen inside the region, like how should it depend on the time extent of the region versus the area of the region and so on. But this approach is going to kind of tell us that it is this area that is controlling what can happen inside the region. Yeah, so that side should become more clear as I keep going. Hopefully that answered your question.
Yes, no, it's obvious that if you have more time, you can compute more stuff. Now, if you have more volume, you can say, like, I have more resources, but it's not obvious that they are both the same. Like, if I increase the length by something, it's the same at the time.
Yeah. It's not totally clear from a bulk perspective why it should be this area that controls it, but somehow this is like the one well-defined quantity that you can pick out from this scattering region, and then it turns out to have a natural sort of dual quantity in the non-local computation picture.
Yeah, thank you.
Yeah. Right. So yeah, okay. I was saying that the quantity in the bulk is this thing's area. The quantity in the boundary is the mutual information in this shared state. Right. So in the space-time picture, that's the mutual information between these two diamonds, V0 and V1. Okay. So then the sort of quantitative restatement of what I was saying is that whatever is computable inside of some scattering region with some area A should be computable in the boundary, or computable non-locally, using a resource state. Oh, sorry. Okay. What I should have said is that this quantity, this mutual information in this state, you can do a calculation, say using the Ryu-Taganaki formula. And what you'll find is that that thing's mutual information is very closely related to this thing's area, the area of that surface. In general, they're always of the same order. In the vacuum state, they're actually equal. Okay, and so yeah, this seems to be the corresponding quantity in the boundary. Right, and then the statement is just that if you can compute something inside the scattering region with some fixed area, it means it's computable in this non-local form, or it has to be computable in this non-local form, using a resource state with an area's worth of correlation. Okay. Yeah, and so that's how I want to try and constrain what can happen inside the region. Is that clear? I got slightly jumbled, so maybe I'll pause for a second. Okay. All right, so I will keep going. Okay. So just for one slide, I want to step back a little bit.
Sorry, Alex.
Yeah.
Go back to the previous slide.
Yeah.
What were the V1, V2 regions? The mutual information V0, V1. Sorry, V0, V1.
How are they defined? How are those regions defined?
Yeah. I think you showed it, but oh, there we go. Okay, thank you. Good.
Yeah, so it's like V0 is the future of C0 in the boundary geometry.
For sure. Yes.
Yeah, that's
Yes,
right.
thank you.
Okay.
Sorry, I have a question.
Yeah.
So in the next slide, when you define this correspondence, yeah. So in this small rectangle on the bottom, you mentioned a resource state. So when you say resource state, are you thinking of some operation, and you're saying this operation as this non-local computation, or does that question make sense?
Yeah, so I'm thinking of like this computation happens non-locally in the boundary. To make it happen, you need some correlation in this state. I'm thinking of, one way I can phrase that is just by saying that that state of the CFD is acting as some resource for me to implement a non-local quantum computation.
Oh, okay.
Yeah.
Thank you.
But I guess the question is it necessary?
Yeah, okay, so for certain computations that happen in the local form, you can actually prove that
I see.
for each qubit of input, so say there's a specific computation with n qubits of input flying in on each side, you can show that that computation requires a mutual information that's linear in n.
I see. Thank you.
In general, we know very little about lower bounds. We expect that generically you do need entanglement, but we can only prove it in very specific cases. Yeah. Okay. Any other questions? These are good questions.
I have a question, Alex.
Yeah.
So until now, you have been considering holographic CFD on a sphere, but would it work even if it's a flat space?
The audio is not coming clear,
Oh.
coming through super clear. Sorry.
Yeah, can you hear me now?
Yeah, a little better. Yeah.
So until now, you have been talking about CFD on a sphere. So C1 was like periodic.
Yeah.
Right, but if it was like a space, and I can imagine that C0 and C1 are like very far away, and I can take R0 and R1 to be very far in the future, so that V0 and so wouldn't the mutual information be zero in that case, like in the asymptotic limit that regions are far away?
Right.
Does that mean that don't do any computation?
Yeah, good. Okay, so there's an interesting theorem, which is sort of implicit when I make this statement, which is that, so, okay, yeah, we have proved a theorem that says that if this scattering region, J, so I'm calling it J1212 because it's the intersection of, or sorry, it should be 0101, right? Because it's the intersection of these light cones. If this thing is not empty, then it actually implies that the mutual information will be order 1 over G Newton. So there's two ways to think about this. I originally found this statement because I was thinking about non-local quantum computations, and I was using the statement I was saying before of, for certain computations, for every qubit you throw in, you need like 1 unit of mutual information. You can use that fact to prove this statement, or just within general relativity, you can show that the existence of this causally defined region implies that the Ryuta-Ganaki surfaces enclosing the union of V0, V1 take on this kind of configuration, which is equivalent to the mutual information being order 1 over G Newton. So yeah, you described a particular scenario where you were worried that this would exist, but the mutual information would be small. It turns out you can't geometrically construct such a thing.
In any state.
That's right. Any state. So, well, I mean, yeah, I'm assuming that there's a bulk geometry. So I'm thinking about states with geometric dual dispersions. But yes, that's right. The quantum information reasoning here is just using the causal structure in the boundary and basic facts about quantum mechanics, like it's unitary and so on. The relativistic proof is relying on the null energy condition. So the proof is for bulk states where the matter satisfies the net. Yeah, that's right.
Thank you.
Yeah. Okay. Yeah, so the clearest description of this part of the work is in this paper with Jeff Pennington and myself and John Soares, if you're interested in that. Good. Any other questions? Happy to keep going. There's parts at the end I can cut out if I'm over time and stuff too, so feel free to interrupt. Okay. Okay, yeah, so yeah, I just wanted to step back for a moment and think about what happened here in a more general perspective, right? So we had some question about quantum information processing in the context of gravity, which in particular was what computations could happen inside the scattering region. We were careful to, first of all, ask that question within a holographic spacetime, and second, ask it in a sort of boundary anchored way where the inputs came in from and went out to the boundary. And by doing that, we could translate it into some other question in the conformal field theory that doesn't involve gravity. And there I can just think about sort of regular quantum information theory. That process you could repeat for other questions, right? So we asked one question here, but you could, think of this as a general tool for trying to understand how quantum information works or how information processing works in the context of gravity. Okay. Another comment is just that this same kind of perspective of thinking about sort of operational information processing tasks from the bulk perspective and relating them to equivalent tasks in the boundary perspective is a tool that me and collaborators have been using in other contexts. So one thing that we've been doing with this is using it to relate features of bulk geometry, in particular causally defined aspects of geometry, to features of entanglement in the boundary. So this theorem I was just describing on the last slide is an example of that, where you say, if this intersection of light cones exists, then the mutual information is large. Right? So that's another direction we've been taking this. And then closely related to that, if you combine the statements that you get here relating entanglement and causal features of geometry with the Ryo-Takanaki formula, which relates entanglement to space-like surfaces in the bulk geometry, then you end up with just geometric statements about ADS space, right? Relationships between extremal surfaces and light cones. Those statements that you get out are new statements people hadn't noticed before. They're things you can just prove in general relativity, or you can understand from this information theoretic perspective. So that's also kind of a nice concrete outcome here, is just that you learn some new interesting facts about gravity and ADS space. Okay, but yeah, these are not directions that I'm exploring in detail in this talk, but yeah, I'm happy to talk about those more in the questions or so on. Okay. All right, so now I want to think more about this idea of non-local quantum computation, and in particular try and understand the entanglement, or how much entanglement is required to do them, right? And okay, let me sort of recap what the question is here. So we're thinking about computation from two different perspectives, either this local perspective as it happens in the bulk, or this non-local perspective, right? And the question that we're interested in is, what is the property of the local computation that controls how much entanglement is required to implement it non-locally? Right? And the basic suggestion that I want to explore is that it could be the complexity of the local transformation that controls its entanglement cost. Okay. There's two reasons to explore that. One is coming from the quantum information side, which is that for the existing methods of going from the local transformation to the non-local one, the amount of entanglement that those methods use turns out to be related to some kind of a measure of the complexity of the transformation. That doesn't establish this connection, strongly. It just says that in the protocols we can come up with, which need not be the optimal ones, in the protocols we can come up with, there is this complexity entanglement relationship. Okay, so maybe in the optimal case that's also true. The second reason to explore this is that if it's true, if the complexity of the local thing controls the entanglement cost implemented non-locally, then it would actually imply Lloyd's idea that gravity constrains complexity. And why is that, right? Well, we'd say that a given region has a particular area. The area controls how much entanglement is available on the boundary to do computations in that region. If an upper bound on entanglement puts an upper bound on complexity, then it bounds the complexity of what can happen inside the region. Yes, there's these sort of two very different lines of reasoning that are both kind of converging on this idea that complexity should control entanglement. And so that's what we'll try and explore. Okay, good.
I'm a little bit confused by the fact that, so when you say complexity here, do you have in mind circuit complexity? What, yeah.
I am remaining open-minded about which form of complexity. So I would say that, a quantity I would call the complexity is take any model of computation. So it could be a Turing machine, for instance, and then quantify some resource used by that model of computation. So maybe the number of time steps it takes, or the length of the memory tape that it uses, or whatever you would like. And it should be something of that form. I'm exploring the idea that it could be something of that form that controls the entanglement cost.
But the reason I ask this question is that complexity in the circuit sense of it can grow exponentially large, right? Whereas entanglement cannot grow very large. So when you say controls it, you probably have a very, you mean it in a very broad sense, right?
Well, so
you don't mean that like more complexity means more entanglement, and as the complexity grows,
so the idea would be, well, okay, there's two comments. So one, like on the quantum information side, why could it make sense that that the entanglement cost could in some cases be exponential? Well, say you want to do a transformation that's like an arbitrary channel. The only method known to do that does actually use an exponential amount of entanglement between the left and the right. I suspect that you won't do better than that, but we don't have a proof that that's actually optimal. But so far as we know, you can have exponential entanglement cost in these non-local quantum computations. How could this make sense in the gravity story? The idea would be that if I have some space-time region, I can't do arbitrarily complex operations inside the region because there just isn't enough entanglement in the boundary. So I have an area's worth of entanglement in the boundary. That's going to restrict me to some smaller set of computations in the bulk, in particular ones that don't have this like exponential safe circuit complexity.
I see. So the gravitational setup always come with this constraint in a sense. I see.
Yeah.
Thank you.
Yeah. Okay. So yeah, this is the idea I want to explore. To explore it, I'm going to first of all think about just a really simple example. The simple example is going to be where the computation is a Clifford unitary. Okay. What I mean here by a Clifford unitary is a little bit different than the usual thing. So usually Cliffords are defined as unitaries that are in the normalizer of the Pauli group that acts on qubits. I'm generalizing that a little bit to higher dimensions. So I have Q kits, which are k-dimensional quantum systems, and then we can define some Pauli group that acts on them, and then you define the normalizer, and that's the sort of Clifford set I mean. Okay. So for this example, we'll think about the entanglement and we'll think about the complexity. To implement the Cliffords non-locally, turns out there's a simple procedure, and it uses an amount of mutual information that's given by n times log k. Okay, so it's like a linear entanglement cost. The complexity of this kind of a unitary, we can characterize quite precisely. So in particular, we're going to think about how hard is it computationally to determine the measurement outcome on, say, one qkit of output from a Clifford circuit. The complexity class that captures that turns out to be this sort of strange beast called mod KL. Okay, mod KL is a super obscure complexity class. You've probably never heard of it. If that's the case, just take it to be defined by what I'm saying here. So mod KL is the class of problems that I can solve by running a Clifford circuit and looking at one qkit of output, measuring one qkit of output. Okay. One thing you do need to know about this class is that it sits between the complexity classes L and P. So what this means is I have a Turing machine, and it can run for a polynomial number of time steps. Then that machine can predict your measurement outcome from your Clifford circuit. Okay, so the Turing machine is stronger than the Clifford circuit. On the other hand, if I have a Turing machine that's restricted to a logarithmic amount of memory, then it cannot predict the measurement outcome from your Clifford circuit. So the Cliffords are more powerful than this log space Turing machine. So this complexity class sits between L, which means log space, and P, which means polytime. Okay. So I realize this is a high energy seminar, so maybe I'll pause there and I don't know if did those complexity statements make sense, or?
I do have a question. Do you have some sort of, can you give some more intuition about log space?
Log space. So yeah, I mean, what you should.
Yeah, go ahead.
Are you like comfortable with a Turing machine model of computation?
Sure, but I don't have a sense of logarithmic amount of memory.
Yeah. Are you like looking for a problem?
I'm just saying that, is there some sort of physics? Is there some physical example or anything that?
I mean, log space. Yeah, it's hard. Okay, so I mean, one thing I can say is like, what's an example of a problem that you can solve in logarithmic space? So here, an example of a problem is I have a graph. It's a directed graph. There's two like privileged nodes called S and T. There's some graph. They have directions to the edges. I'm going to input this graph, and the output is like, I want you to output 0 if there's no path from S to T, and 1 if there is a path.
Mm-hmm.
The size of the problem here is the size of the graph, which I could count by, say, the number of edges. And then it turns out I can solve that. I can check if there's a path in log space.
I see.
Yeah.
Okay.
That's one example. That's actually a complete problem. So every problem in the class can be like
right.
easily reduced to solving that thing.
Thank you.
Yeah. Okay. Yeah. So Cliffords have sort of low complexity in that they are inside of the class P. And they have a little bit more complexity, or they're computationally a bit more powerful than this logarithmic space idea. Okay. Okay, so this example is useful to us because it's a case where we know the entanglement cost and we know the complexity. And then the idea is that if really the complexity controls entanglement, then a consequence would be that any other computation I try and do, not just implementing a Clifford, but whatever else, if the complexity is inside of this class mod KL, then the entanglement cost should again be low. Okay. For the Cliffords, it was actually linear. I'm going to allow this relationship between complexity and entanglement to be sort of relaxed a little bit and allow for a polynomial overhead. So what I'm going to require or look for is that any other computation with complexity inside this class should be implementable non-locally using a polynomial amount of entanglement. Okay, that's a consequence of our idea. We're going to go try and test that consequence. Okay. to test this, we're going to use another example, which is called F routing. Okay. So an F routing computation is defined by a choice of classical function called F, which maps from strings of length 2n to bits, either 0 or 1. Okay. The inputs to the computation are a string x of length n on the left, so it's C0, and then a quantum system Q of some dimension d, also on the left. On the right, we get a string y, also of length n. Okay. Those are the inputs to the computation. The outputs is I want you to bring Q to the side labeled by F. So if F evaluated on the inputs x and y is 0, should bring Q to the left. And if F evaluated on x and y is 1, you should bring Q to the right. Okay. This computation, or doing this in the non-local form, is actually the best studied thing in the literature. The reason for that is because it's some of its properties mean that it's especially favorable for this cryptographic idea that I mentioned. So in position-based cryptography, you're trying to check where somebody is located in space. And in that context, this is a very helpful thing to think about. And in particular, it turns out that implementing this thing non-locally corresponds to cheating in that cryptographic scenario. And so people are especially interested in understanding for a given function, how much entanglement does it require to do it non-locally, i.e. to cheat? Because if it's lots of entanglement, then we think that the crypto, and if it's a small amount of entanglement, then it's insecure. Okay. So this is sort of an aside. Okay. So we have this F routing thing, and this is well studied because of the cryptographic application. The best known strategy, or the one that's the most efficient in terms of its entanglement cost, is what's called the garden hose strategy. And the entanglement cost there is interesting. So the number of EPR pairs you need to do the F routing task for some function F turns out to be given by 2 to the memory cost of computing F on a Turing machine. Okay. This is interesting to us, right? Because we want to explore the relationship between entanglement and complexity. And here, at least within the context of this particular strategy, complexity just directly controls the entanglement, right? This is some measure of complexity, the memory cost. An exponential in that is how much entanglement you need. Okay. We were especially interested in what you can compute or what you can do the F routing task for when you restrict to polynomial entanglement. If I want this to be polynomial, I need to put a log in the exponent here. So I'm restricted to logarithmic memory. So the functions that I can do F routing for using polynomial entanglement in this protocol are the functions in L, this log space class that we were discussing. Okay. So that's the best in the literature. Natural question, can we beat it? Can we do better? Based on our idea that complexity should control entanglement, and because of this example of the Cliffords, we expect that we can. We expect that we can do better, right? And that's because in the Cliffords, we could do the complexity class mod KL, and here we can only do L, and L is contained in mod KL, and we actually think it's strictly contained, so it's strictly smaller, right? So according to our idea, this is not strong enough. Another reason that we might think that this is not strong enough is that from this sort of gravity perspective that I was talking about, if L was optimal, or if the garden hose protocol was optimal, then what it would say is that when you try and do computations inside of some gravitating region, you're restricted to using an amount of memory that's logarithmic in the area of that region. That seems, I can't rigorously say that that's wrong, but that seems very strange. We would think it's more like linear in the memory, right? So say the covariant entropy bound would say you can bring a linear amount of entropy into the region, right? So log of the area seems weird. So, okay, this is very heuristic, but given that and this relationship that we think exists between complexity and entanglement, we think we should be able to beat the garden hose and do better. How could we do better? What new tools could we bring in? Very roughly, in in ADS-CFT, we see that it does non-local quantum computations, and we also know that a really important part of the story of how quantum information is recorded into the boundary degrees of freedom in ADS-CFT has to do with error correction, quantum error correcting codes. So we might guess that a natural tool to use here would be quantum error correction. Okay, so that's what we're going to try and do. We're going to say, how can we exploit error correction techniques to do this F-routing task? And can we use that to reach this larger complexity class of mod KL? So let me explain how that can work just with a really simple example. So in the example, X and Y are just going to be 1. And the thing I'm going to think about is just the AND of those two bits. So it's X and Y. Okay. Then what I'm going to do is the following. So I'm going to take Q, which starts out on the left. I'm going to put it into an error correcting code with 3 shares, S1, S2, and S3. And this code is going to correct 1 erasure error. Okay. Then I'm going to specify the protocol by telling you what to do with each of those 3 shares. So for the first share, S1, you're just always going to keep that share on the left. Okay. So Q starts out on the left, the encoding happens on the left. So S1 starts out on the left, just leave it there. In the table I've drawn here, I've explained where each of the shares ends up as a function of the inputs. So we see that S1 is just always on the left. Okay. Good. For share S2, you're going to do something slightly more complicated. So you're going to take S2, you're going to look at X. If it's 0, you're going to keep S2. If X is 1, you're going to send it to the other side. So in the table, we have S2 on the left when X is 0, and S2 on the right when X is 1. Remember that we have this communication round in the non-local computation where I can send things or keep things. I'm exploiting that here. Okay. For the last share, S3, we're going to do something a little bit trickier. So we're going to bring S3 to the side labeled by Y, right? Bring it to the left if Y is 0, bring it to the right if Y is 1. That's a little bit harder though, because S3 starts out on the left and Y starts out on the right. Okay, the way to get around this is you take S3 and you measure it in the Bell basis with some EPR pair shared between the left and the right. After you do that, you get some measurement outcome and you get a system on the right, let's call it S3 prime, which holds the same information as S3 up to some poly correction. Right. Then I take S3 prime, I send it to the side labeled by Y, the left or the right. And on the left, I got this measurement outcome. This is a classical outcome. I can copy it. I'm going to send it to the left and to the right. Okay. So then on the side labeled by Y, I will end up with S3 prime, which has this poly correction. I will also end up with I. I use that to undo the poly at S3 on the correct side. Okay, so when Y is 0, S3 on the right, and when Y is 1, Y is 0, S3 is on the left. Y is 1, S3 is on the right. Okay. Good. So what has this done for us, right? Remember that the code corrects 1 erasure error. So whoever has 2 or more shares will recover Q. So in these first 3 cases, the person on the left holds at least 2 shares, right? And so Q is on the left in these first 3 cases. Those are also the cases where X and Y is 0, and that's when we wanted Q on the left. Okay, so this worked correctly. In the last case, there's 2 shares on the right, and X and Y is 1, and so we wanted Q on the right. Okay, so that was correct again. Okay, so this brought Q to the correct side and completed the task, the F-routing task. Okay, that was fairly detailed. The high-level picture of what happened there or why this worked is that we have some function f of xy, and we have this code, and we exploited the structure in the code of like the pattern of which subsets recover Q and which do not, and we got that structure to match the function. And by exploiting that, we could complete the task. Okay. So we can generalize that. In particular, you can use what's called a quantum secret sharing scheme to construct codes that have like an arbitrary structure of which subsets recover Q and which do not. You can get whatever structure you would like. I think I'm going to be quick on this just because I'm a little behind time. But the sort of punchline is that in quantum secret sharing, I'll explain a little bit. So in quantum secret sharing, you're taking some quantum system, which is called Q, recording it into n shares, S1 through Sn. You have some desired structure, there's some desired pattern of which subsets recover Q and which don't. That structure is captured by what's called the indicator function. So the indicator function takes a string of length n, the string labels subsets. The indicator function is 0 if you learn nothing about Q from the corresponding subset, and 1 if you can recover Q from the corresponding subset. And then what you can do is, if you want to do the F-routing task for a function that happens to be the indicator function for some secret sharing scheme, you just replace this simple code with your quantum secret sharing scheme. And what you'll find is you can then do the F-routing task for that function with an amount of entanglement that's bounded about by what's called the size of the quantum secret sharing scheme. So the size is just the number of qubits in all of these shares. One thing that's nice here is that the size of a secret sharing scheme is a thing that people are usually trying to optimize when they construct secret sharing schemes. They're trying to make that as small as possible. And so you see here that the entanglement cost in this non-local quantum computation provides a lower bound on how well you can do when you're constructing these schemes.
Alex?
Yeah.
In the previous example, in the previous slide, so we would say that the cost of this, the entanglement cost of this is that EPR pair that you shared, so that you could send S3. So there's one entangled pair cost for this. And then when you replace this E, the 3Q thread code or whatever it is that you're using to an secret sharing code with n parties, then you're saying that the cost of entanglement is less than n qubits. Is that what you said?
So here, the entanglement cost, like say in this simple example, the cost would be like the log dimension of this share.
Yeah, yeah.
And a simple upper bound would be the sum of the log dimensions of all the shares. This is what's called the size of the secret sharing scheme.
Yeah, sure.
Yeah, so when you replace this with some more interesting quantum secret sharing scheme, you have a bunch of shares.
Okay, yeah.
At worst, you have to like use this entanglement trick for all of the shares. And so this object is an upper bound.
But here, the point was that one such trick worked, right? One was enough, right? One entangled pair was enough. Whereas like you're saying that the inequality is less than 3, right? Which is, yeah, okay.
Yeah. In general, like you would take Q and you'd put it into a bunch of shares, S1 through Sn, and then some subset of those you'll have to use this entanglement trick for.
Right.
It's not totally clear which subset, so it's easier just to add them all up.
Yeah.
Use the worst case.
Okay.
Yeah.
Thank you.
Yeah. Yeah. So okay. So we're seeing that. Yeah, the entanglement cost in this this non-local quantum computation is providing some useful constraint on quantum secret sharing, which is some interesting, important subject in quantum information theory. Okay, good. So that related this entanglement cost to the size of secret sharing schemes. What we really wanted was entanglement related to complexity. We can piggyback though on a known existing relationship between the size of secret sharing schemes and complexity. In particular, there's this nice construction due to Adam Smith back in 2000, who showed that for a given indicator function, you can construct a quantum secret sharing scheme with size given by what's called the size of a span program that computes F. So, okay, what is a span program? Span program is just some kind of a model of computation, analogous to, say, a Turing machine. And the size of the program is some kind of a measure of the resources used in that model of computation to compute this function. In that way, you should think of this span program size as a measure of the complexity of that. It's some very different measure than, say, like a circuit complexity, but it's still some measure of complexity. Okay. Using that construction and adding a couple of tricks into the kind of protocol I was describing before, you can go from functions that are realized as indicator functions for quantum secret sharing schemes to just arbitrary functions. And what you find is that the entanglement cost is upper bounded by the span program size. Okay. We're interested in which functions can I do this for using polynomial entanglement. It turns out that functions with poly-size span programs are exactly this complexity class mod KL. That's one way to define mod KL, for instance. That fact does two things for us, right? One is that it brings this example into alignment with our expectation from this idea that complexity should control entanglement. Right? Because we said, if complexity controls entanglement, we should be able to do at least the functions in mod KL. And in this example, we've seen that by introducing this new code-based protocol, we can get exactly that. Okay, so this is nice. Yeah.
How much is known about the tightness of these inequalities? Because from the inequality, you would say complexity bounds the entanglement. To say complexity controls the entanglement, you would need a tight bound, right?
Yeah, that's right. So I'm only providing upper bounds, okay, and I'm getting like stronger upper bounds than before, but it's still only an upper bound. And what you would really want to say that complexity controls entanglement is like upper and lower bounds that are close together.
Yeah.
And I don't have that.
Okay.
Yeah. Yeah. So this is somewhere where, yeah, I'm providing evidence, but like, so we can take this idea and it has various conclusions. One conclusion is that I should be able to do F routing for the functions in mod KL. That turns out to be true. So you can say, okay, I think this supports the idea that complexity controls entanglement, but I can't conclude that.
I see.
Yeah.
Thank you.
Yeah. Okay. The other thing this does is, coming back to this sort of cryptographic aside, is that because this particular computation, this F routing idea, was sort of the most practical one in this cryptographic scenario, it means that, and before, the best non-local computation for doing this realized the functions in L. Now we can do the functions in mod KL. This code-based procedure is now the best attack in the literature on these particular cryptographic scenarios. Yeah, so it's kind of fun. I think that me working on this came out of this connection to gravity, and now it has this sort of practical implication. Okay. All right. So that section was all about upper bounds on entanglement cost and trying to support this idea that complexity controls entanglement. The other thing that so now I want to switch gears a bit and think about the other side of the story. So, which is lower bounds on entanglement. Here, the situation is sort of much more challenging, and I'm not going to provide any new lower bounds. I just want to talk about what the consequences of lower bounds would be, both for the gravity side of the story and for these connections to complexity and so on, as well as a little bit about what the sort of prospects are for proving lower bounds. Because yeah, as Nima points out, this is a very interesting thing to try and do. Okay, so I'll start with the gravity side. Here, I want to think about the covariant entropy bound again for a second. So I've drawn this scattering region again. And what I'm going to do is apply the covariant entropy bound and see what it tells me about computations happening inside the region. Right? In particular, what the CEB will tell you is that if you look at the area of this surface along the bottom that we talked about before, that area divided by 4G Newton will upper bound the entropy passing into the region here. Okay, so there's this red face on the front. the entropy that goes through that will be bounded above by the area according to this CEB. Okay, so we get this statement here, right? Using sort of the gravity side of some of these papers I mentioned, so this one with Jeff and John and this more recent one by myself, you can relate that area to boundary quantities, right? And in particular to the mutual information. And the statement that you end up with is that the passing region I'm thinking about this is a constraint on the computations you can do inside the region, right? So it's saying that if my inputs are too large, they just don't fit into the region because they would exceed this mutual information.
Sorry, Alex, do you mind saying it again? Because you cut out for a second.
Oh, okay.
The
Okay,
very
so
ending, the very ending, maybe last 30 seconds.
okay, yeah, sorry. So right, so we have this statement from the CEB that the entropy is bounded above by the area. From these papers and the gravity story in these papers, we can relate that area to the mutual information in the boundary. And combining those statements, we end up with this thing in the box on the bottom, which is just that the entropy passing into the region will be bounded above by the mutual information in the boundary.
Sure.
So in particular, I could think of, my inputs might be in say the maximally entangled state. And so delta S is just n, the number of qubits of input to the computation. So it's saying that I can't do a computation on too many qubits inside of my finite region. Okay. So that statement is coming from the covariant entropy bound, which is a conjecture, widely believed, but a conjecture about the bulk. Part of the perspective of this talk has been to advocate for the idea that we should try and understand constraints on computation in the region by going to this boundary picture and thinking about non-local quantum computation. So a natural question is, can we recover this consequence of the CEB from the perspective that we're advocating for here, right? The story there turns out to be quite interesting. So the answer is almost. So you can almost recover this consequence of the CEB. In particular, what you can get from what we know about lower bounds on non-local computation is this statement here. So it's of the exact same form. It's just slightly weaker because of this numerical factor of a half in the front. Okay. So I think it's already interesting that you can get that. It's also interesting though to ask, can we get rid of this factor of a half and recover exactly the consequence of the CEB? There's a sort of interesting numerical coincidence that comes up there. So the way that you prove this bound is by thinking about what's called the monogamy of entanglement game. So this is some kind of a non-local game where there's various parties, they're split up, they share entanglement. You give them some inputs, you require their outputs satisfy some constraint, and you ask, how well can they satisfy this constraint? So it's similar to trying to say violate a Bell inequality and thinking about how well you can, or how strongly you can violate the inequality from a quantum mechanical perspective. Okay. So thinking about those kind of games, it turns out that if there's a particular result you could try and prove about these non-local games, that would imply exactly this consequence of the CEB. And the result is you try and construct such a game where your winning probability, or your optimal strategy, is no better than randomly guessing. So we know that your success probability will always be lower bounded by the guessing probability. And if you can actually saturate that, then by a sort of numerical coincidence, the math works out such that you would get exactly the CEB with the right factors. Okay. So this is very intriguing to me and motivates, I think, trying to better understand these kind of games, and maybe more generally thinking about what their relationship is to the covariant entropy bound from in the bulk perspective. Okay. Good. Okay. So sort of one last thing. So the CEB tells us this inequality, right? And one consequence there is that if we prove anything stronger than this, right? Like if we prove a lower bound from this non-local computation perspective of the form, say delta S log delta S, or anything stronger than linear, then we're getting some kind of a new and novel constraint on information processing in the presence of gravity. So what are our prospects for proving something like that? I think it's very plausible to prove something like that from the boundary. It's a very interesting direction, but there are some sort of caveats or pitfalls to keep in mind. So in particular, let's return to this F-routing scenario. Suppose that you prove a lower bound on the entanglement costs to do this F-routing task that is some explicit function of the input size, n. Okay. If you do that, because of this protocol I gave, you also lower bound the size of span programs that compute this function f, right? And lower bounds of that form, like explicit lower bounds on complexity, are very hard to prove, and they're sort of a long-standing goal in complexity theory. And there's been pretty limited success in actually proving them. So from one perspective, you could say, maybe this non-local computation perspective is a really interesting way to try and prove interesting statements in complexity theory. That would be sort of the optimist's stance. I think the more pessimistic stance is to say, okay, in our, if we try and prove new constraints on quantum information in the presence of gravity in this form, like in terms of an explicit lower bound, then we're running into these sort of hard problems in complexity theory. And maybe we should pick a different direction, right? Because maybe this is going to be a hard thing to prove. So I think a better sort of idea, and something I'm thinking about, is to try and prove not an explicit lower bound, but a lower bound on the entanglement cost in terms of some other measure of the complexity of F, right? So our upper bounds look like some measure of complexity. Let's try and prove lower bounds in the same form. So long as those lower bounds are not explicit, this won't prove anything crazy in complexity theory, and seems much more plausible. Okay. Okay, so that's everything I want to say. I'll just wrap up, first of all, by summarizing sort of the logic of this talk. So the overall reasoning here is we want to think about quantum information processing in the context of gravity. We restricted ourselves to think about holographic spacetimes, and then we made use of the ADS CFT correspondence to turn those questions into non-gravitational questions. Specifically, we thought about computation in a finite region within the ADS space, and turn that into understanding the entanglement requirements in these non-local quantum computations. The sort of outstanding question there was to understand what controls the entanglement cost in these non-local quantum computations. That's going to control what you can do inside your region. The idea we explored was that complexity could control entanglement. We did that by, first of all, looking at this Clifford example, setting up some expectation that mod KL should be efficiently computable, and then testing that expectation by looking at this other task, this F-routing task, and finding that we could realize that if we introduce this new code-based protocol. Okay. So I think the story I'm telling here is just sort of one particular thread in a really interesting web of connections between quantum gravity and quantum information theory, and all kinds of interesting subjects in quantum information theory, like these non-local games and secret sharing and cryptography and so on, complexity theory. Within that whole space, I think there's many interesting directions to go. I've highlighted a couple that I sort of have in mind. One is to better understand this non-local quantum computation idea. There, I think the sort of outstanding question, the most exciting target, is to try and prove lower bounds on entanglement. Two things there was, one, to try and recover this consequence of the CEB with the correct numerical factors. The route forward there seems to be better understanding these monogamy games. Beyond that, we're interested in trying to prove new constraints on computation in the presence of gravity. And there, the route forward seemed to be thinking about what the right kind of lower bound would be, and understanding in a bit of detail the relationship to complexity theory there, and what that says you can expect to be able to do, and maybe should be wary of thinking you could do. On the other side, We can, of course, look for improved protocols and ask, can we reach still higher complexity with while restricting to polynomial entanglement? I don't have any great new ideas there, but it's something you can continue to try and do. We made a little bit of progress here. And then stepping back a bit, we here asked about one question about quantum information in the presence of gravity, turned it into a boundary question, found all kinds of interesting connections to quantum information theory. We can try and repeat that process, think about other questions about quantum information in the presence of gravity, see what they mean in the boundary, think about what kind of interesting questions in quantum info and complexity and crypto that those raise. Okay, so yeah, that's everything. And thank you. I'll leave out this slide.
Thank you so much, Alex. Are there questions for Alex? Here or online? Is there a question? Oh, okay.
I have a basic question.
Yeah.
One basic question and one naive question. So one basic question is in routing task. I kind of confused, like, what is the erasure? So you're in the routing task, you're thinking of erasure task, right? Encoding Q into S1, S2, S3.
Mm.
But where is erasure?
Yeah, okay, so good. So for the more general thing, we take Q, we put it into some secret sharing scheme, right? Some of the shares, okay, and then what we do is each share effectively gets brought to a side labeled by like one of the bits. So the first share goes to the side labeled by, I don't know, X0, the second one to the side labeled by X1, and so on. We use entanglement to do that in some cases, but the overall effect is that on the left, we obtain the shares S sub I such that like the corresponding bit is 0. And on the right, we obtain the shares S sub I such that the corresponding bit is 1. Okay. So then this is some subset of shares. We should think of all the remaining shares as my erasure error, right? And then we ask, can you recover the logical system from this subset? If you can, then Q ends up on the right. If you can't, secret sharing schemes have the sort of additional structure that whenever a subset doesn't reveal Q, it actually tells you nothing about Q. Mm. And so if everything on the right tells you nothing about Q and the left holds the purification, then Q will end up on the left.
Okay, I see. Thank you. And the naive question I have is, do you know any story of quantum task relating to chaos? For example, so naively, what I have in mind is about chaos bound. And I think scrambling is kind of like the task that you can think of. But I'm not sure, like, do you have any idea or have you thought about chaos task in this context?
Yeah, some process in the bulk that, say, in the boundary is exploiting the features of scrambling or chaos to realize. Yeah, I don't. It's a good question. I mean, I think one maybe related comment is that you can try and, so here I was thinking about new strategies for trying to do these non-local quantum computations. One feature that I introduced, which like very loosely is motivated by thinking about ADS-CFT, is asking, how can we exploit error correction to do non-local quantum computations? Because error correction appears in ADS-CFT. You could say, okay, one interesting physical feature of ADS-CFT is there's this relationship to scrambling physics and chaos. Can I somehow bring that in to do non-local quantum computations? It's I think a totally reasonable question, but I don't have any good ideas about it.
Okay, thank you.
I think I have a naive question also. So I think in holography, like complexity is conjectured to be like dual spatial volume. So
Yeah.
here you're saying that, or you're showing how complexity is also controlling entanglement, which is like the entanglement entropy is related or due to the spatial area. So would that mean that there's some relation between complexity and area directly?
Yeah, so the appearances of complexity here are very different. So yeah, the complexity equals volume or action story is about complexity in the boundary, and then volume or action in the bulk. Here I'm thinking about the complexity of what happens inside some subregion of the bulk, and supposing that, well, arguing that that's constrained by entanglement between some particular regions in the boundary. Yeah, so because the appearance of complexity is appearing on two different sides here, it's not clear to me that there's any relationship to the usual appearance of complexity in ADS-CFT, but yeah, I don't know. Maybe there's some further reason to think so, but at least naively, they sort of don't relate to each other.
Thank you.
I have a question, Alex.
Yeah.
So in the setup that you use, you have a bulk region and the region you call J, and
Yeah.
there was a single safety boundary. But let's suppose you have something like a thermofeed double where you have two boundaries and you have a bulk region there. Can you talk about like P0 and U1 the setup and?
Yeah, so this would be an interesting scenario to think about. So of course I could say put my input points down here at an early time. I could throw in my inputs, right? I have them meet up in here. Some computation happens. Now, of course, the issue is that the outputs don't reach the boundary again. And so I can't really probe what's going on here from a boundary perspective in the same way as I was doing in the single-sided or like the one boundary case. You could, think about this sort of traversable wormhole story. You could introduce some coupling between the left and the right. Then, okay, these signals can get out. And I could maybe put my output points here. Okay. Now it's sort of confusing though, because how do I define, say, V0, right? That's supposed to be the future of C0 and the past of R0 and the past of R1. But the past of R1 here, R1 has this non-local coupling in its past. And so I think you should consider like all of this also in the past of R1. And so now V0 and V1, I'm not quite sure how to make sense of them. I mean, I suppose they're the entire left and right CFTs. But it's a little bit confusing.
But this is a question which will make sense from the bulk point of view, but it can't make sense easily from the boundary.
I mean, yeah, I think it makes sense.
R0 and R1 can be a bulk point, right?
R0 and R1, they should be boundary points to sort of relate what happens in the bulk and the boundary. You kind of want your inputs and outputs to come in from and go out to infinity. So I mean, certainly you can think about computations happening in the bulk here, but it's a little bit confusing to translate that into a question in the boundary because of this non-local coupling and it messing with your causal structure kind of thing. Maybe it may be possible to make better sense of this than I have. I'm sort of confused about it.
Thank you.
Yeah.
Any last questions for Alex? If not, let's thank Alex again for the wonderful talk.
Yeah.
Thank you so much. Enjoy the sun over there.